I'm joined today by Terry Rudolph, one of the founders of PsiQuantum. And as Sasha mentioned, quantum computing is something that is going to change the world. And PsiQuantum is probably the most important company that no one has ever heard of. But as a co-founder, I'd love to start by asking Terry a few questions about how he got into quantum computing. I mean, quantum physics is not the first thing that most children choose as they're growing up to be their profession. And so, were you tortured as a child? Were your parents, mean to you? Why quantum computing?
It was never even an option to become a quantum physicist. I was only told about being a doctor or a lawyer. And I didn't know anything about, quantum physics really until I decided I'm going to go to university. And I just chose the hardest subjects that there were, which were math and physics. And it was just because I was an arrogant 17-year-old and wanted to, prove I was smart enough. And yeah, it's one of those things where suddenly at some point, and for me, I was 3 years into this degree and doing a course in quantum physics, and the lecturer on the very last lecture of the term, he, as a treat, gave us an exposition of a theorem in quantum physics called Bell's theorem. And that's what counts as a treat for a physicist. And it was just something so shocking to me that at that point I just couldn't believe that it was true. And I thought, I've got to understand this. It ruined my whole examination period because all I did was think about this theorem. And at that point I decided, okay, I'm going to become a quantum physicist. And it was very much a singular moment in my life.
And so you basically were challenged by a concept that wasn't provable at some level, that normal humans couldn't understand, and that decided that's what I'm going to do for my life?
Yeah, absolutely. And the best thing you're going to do if you're going to do something just pontificate uselessly about reality and nature and so on is become an academic. And so, yeah, that's what I did.
So speaking about academics, when PsiQuantum was founded in 2016, you were a tenured professor in the UK of quantum physics. Isn't that like the end of the road? Isn't that nirvana for a professor to be tenured? Like, why leave all of that, move to Palo Alto, and found a startup?
Well, I partly blame you for that. I'll let you know. It was never something I contemplated my academic career. I was very happy being a professor. I mean, there's obviously problems in life as an academic. But when we got to a point where we realized, maybe building a quantum computer using some of these ideas that we've been playing around with is actually possible, really there on the horizon, using technology that we could see coming. We started trying to work out how much money it would take and what the resources would be and so on. And Silicon Valley ended up being the only place where not only could we get the resources, but also the expertise of people. And, it wasn't a trivial decision, but my head of department at Imperial College said to me, just go and do it, and don't try and keep your students and so on. Just take leave and go and see if you can get it going. And, fortunately, both you and he said, you've got to throw yourself into this 100%, and so that's what we did.
And so PsiQuantum was founded with the mission to make a useful quantum computer, actually the first useful quantum computer. What does that really mean? And the definition of a useful quantum computer, has that changed over this 9-year span of the PsiQuantum journey?
For us, the definition has always been, that it has to do something that there is no hope of ever doing with classical high-performance computers. And that includes high-performance computers running AI or any other kind of algorithms out there. And that is the promise of quantum computing, that we can do something, solve problems, tackle, challenges that there is no other way, even if we turn all of the silicon in the Earth's crust into a supercomputer. And so for us, that really hasn't changed. We're a singular company, singular focus, and yeah, that's what we're going to do.
And so PsiQuantum has mentioned that they think 1 million qubits is the beginning of useful. And yet, we have people like the Google Willow device with 105 qubits that say they've achieved quantum supremacy. So isn't that interesting? Why a million when 105 seems pretty good?
Well, it is scientifically very interesting. I think they've made some very nice quantum states. But what they have is, at best, something like having a calculator when you want a programmable computer. You want something that's universal, programmable, can solve big problems. The Willow device is at least 10,000 times too small to do something that we can't do with, that's useful in this whole set of things, kind of problems, impactful problems that we want to solve. And so, yeah, it's beautiful physics, and I can give you sort of analogies to it, but it's still very far, and they know as well, it's very far from the kind of machine that's really going to be a new technology for humanity.
And so if we had a useful quantum computer, what would we be able to do that we can't do today?
It's difficult to know when you don't yet have the ability to solve the problems, but the two big areas in which I would say we know quantum computers can really outperform classical computers are chemistry, biochemistry, chemistry, and material science. And those are areas which have some quantumness in them anyway. And you might think like, oh, but humans are really good already at chemistry and material science. We're very good. Why are we going to do something that's so great? And I'm going to steal an analogy from my CEO that I heard the other day. If you look at this building around us, look at the materials, the steel, the concrete, the glass, everything, the amount of energy that was expended in designing these materials. We've spent thousands of years getting better at building buildings. And it would be easy to be impressed by where we're at with that and say, yeah, we really understand material science really well. And yet, this building didn't grow from a tiny seed that fell on the ground, that took the energy of photons from the world around it, that took chemicals out of the air and grow 1,000 feet tall. And this building's not going to be around in 1,000 years like many trees will be. Our understanding of chemistry and biochemistry is so limited. We're just right at the very, very beginning because we can only understand a tiny, tiny corner of the quantum state space that classical computers can access. And with quantum computers, we want to open up that state space so that we do understand all of these things. And so where that's going to take us is hard to see, but I can see it's a vast horizon of things out there for us.
And I'd be remiss not to say, can't AI just solve all of our problems? I mean, enough compute and enough data, we can answer anything with AI.
Yeah, I think, it's legitimate to say like AI is going to have an impact in both material science, chemistry, and many of the other areas that quantum computers will have. But there's big fundamental differences. AI is still classical computers, and there's extremely good reasons to believe that no classical computers can solve certain problems. But it's more that a quantum computer is also operating from first principles with equations that we know, so we get a solution and we know the quality of the solution that we get. And so what this means is that, if unlike the case, let's say an AI can give you 1,000 answers to some problem, like make these chemicals and so on, a quantum computer can actually tell you and evaluate, hey, here are the ones that are good, here are the ones that are bad, and we can have confidence in that. Similarly, a quantum computer can generate data for AI. So if you want to find things that, synergies between AI and quantum computing, then you look for things like, well, a quantum computer, instead of doing a messy, expensive experiment where things might go wrong and things might be hard, you can run quantum simulations of those experiments and generate data that you know exactly how good it is, and you can access things that you just can't access in hard-to-do experiments in the real world. So quantum computing does, I think, have some strong overlap with AI, but then I think there's many problems that we're going to go to that are really sort of completely orthogonal to this kind of trajectory.
I mean, we're talking a little bit about the difference between discovery and design. In material science, in biology, a lot of things are discovered.
Yeah.
And AI can help us even discover more things, but can't necessarily help us design them or know whether that's an accurate solution or not.
Yeah, you're not going to get a deep understanding of what you're doing. AI is a bit like a black box. It'll give you solutions. Obviously the technological impact's important, but I also feel sort of philosophically that we need quantum computers to help us deeply understand quantum theory itself and what the opportunities there are. I don't think, if you think about the Industrial Revolution, would the Industrial Revolution have happened if when the apple fell on Newton's head, some voice from heaven dropped a black box on Newton and said, here, this thing will compute any trajectory you want of any apples flying around. This just would not have happened. And without that deep understanding of the scientific theories of classical physics, electromagnetism, thermodynamics, Newtonian mechanics, we would not have had that first industrial revolution. And we know that there's this huge quantum state space out there that we currently access, tiny, tiny fraction of. And we don't have the ability to understand that. And dropping a black box that kind of gives me solutions to certain special cases is not going to help me get that understanding. So if we want another, like a quantum industrial revolution, we need a quantum computer. It's the only thing we know that can get us across that threshold.
And PsiQuantum has announced that they're going to dedicate some amount of their first computer to solving climate challenges. Is quantum computing useful in the climate challenge?
I think many of the challenges, I'm not an expert in this area, but many of the challenges to do with climate change are challenges to do with chemistry, biochemistry, material science, and so on. We just saw this example of photosynthesis. Right now, roughly 2% of all the world's energy is spent. Like, this is just a crazy amount of energy is spent taking nitrogen from the air and making fertilizer for plants. And plants can do it with much less energy, but obviously not that efficiently. Just even a single application like that, if we could understand nitrogen fixation, devise new catalysts, solve these problems, who knows what the impact will be long term, and that's just one very small example.
So even when you started PsiQuantum, small quantum computers existed of different forms. We've had these small quantum computers for a long time. Why hasn't someone just built a really big one? What's the problem?
Yeah, so the thing about quantum effects is that as you shove more and more things together, typically the quantum systems all kind of interact with each other, and then in an uncontrolled way, they add noise, and this destroys the very quantum effects that you're trying to see. And if that wasn't true, we wouldn't actually be able to see ourselves as classical objects, because ultimately we're also quantum objects. And so the scaling up challenge is a real challenge. We build our quantum computer out of photons. Photons don't actually interact. That gives us some other challenges. But it does mean that we can scale up from the small systems to the big systems very much more easily by just connecting together larger and larger numbers of photonic chips with standard optical fiber. And so that's the whole reason, that was the sort of bedrock thesis for the company.
And so if you're not using a photonic approach, you run up against other scaling laws?
Yeah, and you think, there's still, for most approaches, there's still a lot of unknowns as to how they're going to build systems that are big enough to cool these things and so on. It's annoying to have this overhead for error correction, but honestly, like if you think about the transistors in your phone right now, they're all, the 0 and 1 state of the transistor is itself made up from more than millions of electrons. It's trillions of electrons in some configuration. And the different bit values is a bunch of electrons in a different configuration. And it's the same with the quantum computers. We need about 1 million qubits that we can control the configurations to make the logical quantum states from which we want to do the computation. And it's just unfortunate that nature is such that the different configurations in your phone are fairly stable against fluctuations and perturbations, but the different configurations in the quantum computer are not. It's almost like nature kind of wants us to have Instagram, but not quantum computers. And so, this is the thing that we have to push up against all the time.
And so you mentioned error correction and the difference between physical qubits and logical qubits. And as the chief architect and an expert in information theory, quantum information theory, error correction is kind of your problem.
Oh yeah, absolutely. And it is a problem, because we don't have a quantum computer yet to help us solve some of the problems that we need. So it's a little bit like Turing designing classical computers and using by hand, sitting there with paper and trying to work out what they're going to do. Quantum computing is in a similar situation, but error correction has improved a lot. We've brought many things, many numbers down, like as to what size of machine we need. We've improved the threshold of noise performance that we can tolerate. But the main thing that we've done is actually work out that once we have this 1 million qubits, we will be able to get a lot more computational power out of it than at the time when we founded the company that we thought we would be able to get out. So that has actually been a very nice thing to discover.
And from a rough scale point of view, how much is your error correction improved, in orders of magnitude from when you started to where you are now?
At least 3 orders of magnitude in terms of the size of the stuff that we're building for a given number of logical qubits. But yeah, there's many axes in which different things trade off, and so it's hard to be precise. But
and is there still room for improvement?
There's still a lot of room for improvement. I think for us the biggest improvements will actually be technological. If we can just get a room temperature photodetector that's good enough, suddenly the whole machine shrinks down in ways that I dream about when I fall asleep at night.
So, there's been reports that you're building a machine in Australia and a machine in Chicago that will have 1 million qubits and will turn on in less than 3 years.
Yeah, is that a question?
So,
or is that just a statement of disbelief?
It just, I don't know. I'm gobsmacked that we live in a world where we may actually have a new class of tools, useful quantum computers, in 2 to 3 years.
Well, the engineers have promised we'll turn it on. They haven't promised me yet that it'll work. But yeah, I think it is amazing. I think there's a lot of misunderstanding about the progress. Like we already, we've made thousands and thousands of wafers of chips and millions of components and tested them, and we're doing it all in the same kind of processes, foundry processes that are used to build the chips that go into a data center or a supercomputer. And so, data centers and supercomputers, they're fundamentally scalable. Like silicon manufacturing is the only thing humans know how to do where you can build machines built from trillions of components and have them work. Now, obviously, no one's ever built these things before. We're both designing the chips as well as the infrastructure. There's a lot of big challenges to putting it all together and making it work in a single go. But once you have that really every single thing that you're building is being done in a truly scalable silicon manufacturing process, then those numbers are just not as scary as they might otherwise
Is that
seem.
why you partnered with Global Foundries?
That's why we partnered with Global Foundries. I was very naive when we came to the Valley. I knew nothing about silicon manufacturing, and you'll often hear people talk about, oh, we've got our own foundry. Many universities have their own fabrication facilities and stuff, and these things are absurd relative to the small number of really tier 1 foundries on the planet, of which there's very few. And so we spent a few years just convincing both ourselves and them that we would be able to manufacture in a facility like that the kind of chips that we needed with the performance that we needed. We had to introduce 2 materials to their process lines. We had to introduce a whole bunch of other processes and so on. And so none of that would be possible without working together with, the Global Foundries. We're not a customer of theirs. We really work together with them, and I think we're probably the most exciting thing that they have going, honestly.
And so these first, 1 million qubit machines, help us understand, what do they look like?
So they in many ways, will look like a data center. You saw a sort of artist rendering from the outside, a massive warehouse-sized facility. What you probably didn't notice in the background there is that there's a very large cryo plant there. It's a cryogenic plant that will produce liquid helium, which is seems pretty cold. It's actually fairly warm for a quantum computing system, but still a very cold fluid. We need a lot of it, and that will be pumped around. So the big difference with the data center will be some of the chips have to be cooled by liquid helium, which then has to come through the whole facility in pipes that will look similar to this, but obviously be a lot better shielded and a lot colder, and drop liquid helium down the back of all of these cabinets. And that is, obviously makes that infrastructure problem more challenging than a data center for sure.
And so what does a rack look like, and how many racks are we talking about?
So the racks are slightly taller than me. They have about 20, equivalent of what we call a side blade, but it's just a unit that goes in on each side. That unit is sort of cross-section something like this, and maybe about 1.5 meters long. And it's sort of many of those things, like roughly 40 of those make a single cabinet. So, it's a single cabinet is close to the size of a bit less than the footprint of the stage that we're on now. And then, we need hundreds of those cabinets in order to get really a useful quantum computer.
And how are they connected?
And they're all just connected with optical fiber. Yeah. And there's a lot of classical computing that has to do the control between this thing and be coordinated and synchronized across the whole machine. So I shouldn't trivialize the amount of high-performance classical control and logic and so on we do is also pretty large.
And so when you have the first one of these and you turn it on in the next few years, does that make making the next one easier?
Well, I very much hope so, because, there's this whole bootstrapping thing I think is really important to understand. Like, you're building a quantum computer using quantum physics that we can't completely simulate extremely well. So having a quantum computer, of course, the first thing you want to do is use it to go and help you make a better quantum computer. Of course, you're going to be fighting the corporate people in the company who are selling that time to someone else to get money by some other mechanism. But at least for photonic quantum computing, there are a few things where we see, like if we just had a better material for single photon detectors, we could have a room temperature quantum computer. I think photonics is the only approach that can give you a room temperature quantum computer like that. And we know it's possible. Your eye can detect single photons, and your eye is not at liquid helium temperatures. So, these things are possible. We just, need to sort of empower ourselves by crossing this threshold of really having large-scale quantum computation.
The better tools can give you an exponential improvement in the next set of tools.
Yeah.
So what advice do you have for academics that are contemplating starting a deep tech startup?
Well, yeah. So one piece of advice would be to find very good initial VCs who actually understand how hard it is, whatever it is that you're doing, and are supportive, and basically are in there because they're genuinely interested in the stuff, the physics, the science, and engineering of what you're doing. I think that was important for us. You guys in Redpoint were really been amazing for us in that regard. As an academic, at least my initial thought was, well, I'll keep, my group at Imperial, maybe 20%, 30% of my time, and then come to the Valley for the rest of it. That would have been a big mistake, and my head of department and our initial investors both basically said, no, don't do that. And I think that was great advice. You've got to throw yourself into it 100%. It's going to be a hard enough job as it is. You can't keep all those connections to academia. It just doesn't work. But you will have, in industry, you do have some big advantages, not just resource-wise, but just the fact that you can hire people who already have a PhD. You're not training them. You're not trying to spend years getting them up to speed. You're taking the best people anyway. And then, at least for us, one of the nice things about tackling science with a whole bunch of smart, PhD students or postdocs or whatever they are, is that you're all now working on a singular goal. When I was in academia, I had a big group. I had 20, 30 odd PhD students over a couple of years, and they were all working on their own thing. I was the only unifying piece of what we were doing. When you're in a company where everyone is working on the same goal, everyone benefits from what everyone else is doing. And I think it creates a much nicer atmosphere in order to try and tackle these kind of problems.
And we couldn't be more excited about that goal and having, being able to live in a quantum computing world in the next few years. Thanks for making it happen.
Thanks a lot, Bruce.